Hello and welcome to this video on the recovery process of a partial liver dissection. Your liver can be partially removed for a range of reasons. A cancer, donation, biopsies and more. Unlike most other organs that struggle to heal, your liver is very resilient. It can recover to some extent from these processes that cause sudden and large-scale damage. What the liver struggles with is smaller but chronic amounts of damage, such as alcoholism. The question is, what makes the liver so much more resilient to short-term or acute damage? To understand what's going on, we first need to understand some of the liver anatomy and physiology, which may be frustrating, but it's kind of important. To start with, there are hepatocytes. These are the functional or working cells of the liver. Each is more or less a hexagon in shape. Each corner of the hepatocyte is met by two other hepatocytes. At this juncture, we have three vessels. These three vessels are known as the portal triad. Each triad consists of a portal vein, hepatic artery, and bile duct. The hepatic artery brings blood into the liver and therefore hepatocytes from the aorta. The hepatocytes process the blood coming in a manner of speaking. What happens is that the blood content, such as pharmaceuticals, metabolites, nutrition, and all kinds of other content flows through the liver and it enters the hepatocyte. The hepatocytes process it, either by enzymes, converting into something else, and any other metabolic processes that might be required. The blood going into and then later out of the liver via the portal vein carries this away and towards the heart to disseminate it across the human body. The hepatic artery will bring blood directly from the aorta, and the portal vein will bring it from the digestive tract in. This therefore allows the hepatocytes to be given a constant and very extensive supply of blood for metabolism. The only exception to this is the bile duct, the last part of the triad. What happens with the bile duct is that it will take lipids, salts, and enzymes out of the liver and store them in the gallbladder for use in digesting lipids in the duodenum. This is more or less the liver taking things that otherwise can't be used as they are or packaged to be used as they are and sending them to somewhere where they can be useful later. This system of three hepatocytes and a triad of vessels is the basic unit in your liver. It will be repeated both horizontally and vertically throughout most of the liver and will take up pretty much all of the space. Admittedly, it's somewhere between 70 and 80%, but it's more or less most of your liver. There are two areas where an exception exists, these being the vena cava and the falciform ligament. The latter of these separates the left and right lobes, the right lobe being much larger than the left lobe, as the left lobe is partially blocked by the stomach. The vena cava itself is the primary blood vessel just above the liver and just below it. The key thing here is that the lower part of it, or the inferior vena cava as it is called, and the superior vena cava, or upper vena cava it is called, both bring blood into the heart. The inferior vena cava brings all the blood from the GI tract and lower extremities together and returns it to the heart. The superior vena cava collects blood from the upper extremities, which includes your arms and head, returning it to the heart. With the major elements of the anatomy understood, we need to delve further into the hepatocytes to see how they make the liver so much more resilient to being damaged. Hepatocytes are very capable. Not just can they break things down, but they can build them up. This is the basic meaning of metabolism. Metabolism can be catabolic, or it can be anabolic. This means it can either build up or break down. Each hepatocyte is made up of a lot of materials that constitutes the rough endoplasmic reticulum and ribosomes. Ribosomes are what make the rough endoplasmic reticulum look rough. The reason for having so many and so much is they help to convert or modify proteins in various ways. The liver has a very major role in producing proteins for the human body, and especially a surprisingly large amount of blood proteins that are unrelated to the immune system or to cells as a whole. That makes it possible for the hepatocytes not just to make a lot of protein, but later through the smooth endoplasmic reticulum, which has no to few ribosomes, it can produce lipids, carbohydrates, and hormones. This allows for a almost specialized and dedicated production cell within the liver. Understand that they go through a lot of wear and tear, but because of this, they're also very able to quickly and easily replace themselves. And that's really important here. Because they are more or less, let's say, designed, to use a very vague term for now, and probably the most inaccurate one, they very quickly replace and repair damage. that's because of what they do. They produce so much that, like a factory that's always producing something, there's always breakdowns, and they can't afford to have those breakdowns last for very long, so they quickly replace broken parts. This is the basic of cell anatomical function in the liver, so then we need to look at how this plays out when you have part of your liver removed. Well, actually, it does cope really well, and you can take away a surprising amount of your liver. Up to 2/3 of your liver can be removed, and it will still function. Of course, this is an ideal average, let's say. It assumes things like perfect health, good age, no complications or comorbidities, and so on. Still, to be able to remove up to 2/3 or the vast majority of your liver and still have it grow back to more or less exactly the same size and function with relatively no issues at all is kind of crazy. The reason for this being important is if you choose to be, say, a living donor, that is, donating part of your liver to another person while you're both still alive. And this is in contrast to when you wake up in an ice bath and have your entire liver, kidney, and so on missing. Or you don't wake up at all, and your liver, kidney, and so on goes missing. The way the liver does this, and what triggers it, first of all, is that blood flow gets reduced to one part of the liver. And what happens is the liver will start to increase in size to compensate for this. That is, again, those cells we mentioned earlier that are so very capable of being replaced easily. It can, due to the nature of what it is, simply increase in size. They have all the necessary materials internally to do so. But after a certain point, hypertrophy or increase in cell size isn't really going to work out. It can to a certain extent, but there is a diminishing return after a certain point. So you start getting those cells dividing and producing immature cells. Now, these immature cells work, but they don't work very well. They just don't have the full suite of functions. And so, over a few days, they will mature and begin developing exactly the same as a normal mature hepatocyte will. And so, over a few days, you see that you actually begin to get recovery, and fairly quick recovery as these cells multiply to make up for what's been lost. And since there's no blood supplied to these new cells, they undergo further, let's say, multiplication or proliferation. Now, angiogenesis, or the creation of new blood vessels, will occur, but it takes time. And this is a major reason why, let's say, patients, particularly cancer patients, who have liver or part of their liver removed, will find that about a month after surgery, about half of the liver can be completely replaced. And that's kind of amazing. Remember, the liver is a fairly large organ, and to have the entire thing basically grow back to its previous size in a month is really quite impressive. The way this can be done is also a significant factor, though. Different kinds of hepatectomy, or basically a dissection or removal of part of the liver, will be done different ways. Now, most often it'll be done with something like laparoscopic or robotic surgery, and that's simply because you don't need anywhere near as invasive surgery is probably the best word for it. Human hands are quite large, relatively speaking, whereas laparoscopy or robotic surgery only needs very small incisions, something around the size of, let's say, 2 centimeters or about half an inch at most, and sometimes even less. You may need several of these, so let's say 4 to 6, but compared to a large open surgery, that's still pretty good. That also means that there's much less physical damage to the body itself. Yes, you have removed a large part of the liver, but the actual damage to the body around that is minimal, and that means most of the energy, so to say, it can be directed and focused only on recovering the liver itself. But then inside the liver itself, we have certain events that occur in response to the damage. Now, this is going to be a very, very simplified overview of what happens, but when you remove large portions of the liver, particularly when you have to resection it, or similar for cancer, or for a living donation, you have something called phosphaturic mediators that become active. And it's fundamentally a problem that occurs due to the liver being injured. And it increases to put it simply, it increases the amount of damage that is perceived as having occurred. And when this occurs, you get signals that tell the body, we need to compensate for this, but because it's effectively overestimating it, you end up with a much faster and greater degree of recovery. Now this helps particularly in terms of the recovery, but it also does create downstream effects that are less desirable. One result of this, though, is that it appears, at least somewhat, that the healthy or recovered part of the liver has a direct effect on clearing away this material. And because the healthy part of the liver is clearing it away, it creates a negative feedback loop. That is, as the liver recovers, it tells it to slow down the development of new tissues to replace what's been lost, and therefore, you see a diminishing growth rate as the liver returns to more or less its expected size and shape. The other effect we have is simply the earlier mentioned fact that the hepatocytes are already inclined to be able to be easily and quickly replaced, and in a way we can look at it as being not so different from the general process the body undergoes when healing from damage. That is, the usual inflammation, immune cells, chemokines and such come into play. What makes the liver able to recover so much better than other tissues is that it has all of the necessary materials in the form of nutrition and cells on hand. You have nutrition being delivered from the GI tract through that hepatic portal vein. You have other nutrition and various things being delivered via the aortic and then into the hepatic artery. And all of this means that they can quickly start doing what needs to be done. You get delivery of various immune cells that will play a role in removing waste and increasing the rate at which cells divide and repair themselves too. And all of this means they can quickly divide and refill the lost parts of the liver. And because of the rate at which they're dividing and how quickly it occurs, you get minimal scarring developing. With a minimum of scarring, you don't get any interruption or blockages to the various vessels within that triad inside the liver itself. To use a rather terrible analogy, it's rather like having your car break down in the mechanic's workshop. Everything you need to begin fixing it is right there, along with the expertise to do so. That means that rather than facing delays getting your car to the mechanic, diagnosing the issues and waiting for delivery of parts, everything is immediately known, available and actionable, or if it's not, it can very quickly be sourced. Of course, that doesn't mean that there aren't any complications, but when you look at the value of being able to effectively heal your liver from 1/3 to a full liver in about a month versus, well, in some cases having almost no liver at all, the loss to benefit ratio shifts drastically in favor of this process. This is how and why your liver recovers from being resectioned, dissected, and hepatectomies with relative speed and ease. But as mentioned, there are some certain complications, but they're outside the scope of this video. Thank you for watching. If you have found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.